Okie dokie, welcome to lesson 7.4 part 2 on solving radical equations. In this video, we're going to do harder examples compared to the previous video. Now, if you watch the previous video, it basically covers the main idea, which is when you have a radical like this, right? If it's an nth root of something or whatever, convert it to a rational exponent and raise it to the reciprocal power. That's all said right there. So we're going to do that, but kind of follow some more difficult examples. And so I've got 4 examples here. They progressively get a little more tricky. So we're just going to go through them one by one. And I think I'll take my time, so this video might be a little long, but I want to take my time explaining this. Okay? All right. So let us start with example 3. So it says, example 3 says, solving creatively without a calculator. So this is kind of continues the basic premise of using reciprocal powers to solve. But sometimes if you don't have a calculator, the numbers get really big and you got to figure out how to deal with that. So that's what we're going to do here. So I've got my current radical all here. It's 25 minus x to the power of 3 halves. If I'm going to raise this to the reciprocal power, it would be a good idea to isolate the radical. I will isolate the radical. Now, I do want to tell you that it's not necessarily mandatory to isolate the radical. In fact, I could take this 1/4 25 minus x to 3 halves, blah, 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 blah. I could go ahead and raise this to the 2/3, but I have to be careful if I do that because this 2/3 is going to apply to this 1/4. And I'll just tell you from both experience and from seeing other people do it in their life, you got to be careful if you're going to do it that way, all right? Because, well, I mean, you just do, okay? A lot of times you'll use this operation, but you'll only use it on this term. Well, it also applies to the constant in front. So if you want to do it that way, by all means, go ahead. But I think it might be a bit easier if you first isolate the radical. So we'll do that by multiplying by 4 on both sides. And this gives me 25 minus x to the power of 3 halves equals 54 times 4. Now, I'm not going to calculate that actually. I could, right? And if you're good with mental math, you'll know that 50 times 4 is 200 and 4 times 4 is 16. So you could say that this is 216. And if you'd like to do that, you're welcome to. But I'm going to use a bit of a different approach on this, okay? You're welcome to do that, though. And 216 is nice, by the way, because that's a perfect cube. But, let's keep going. So now that I've isolated the radical, I want to get rid of that rational exponent of 3 halves. To do that, I will raise both sides to the reciprocal power. The reciprocal power being 2/3. So once I do that, I will raise this whole side by 2/3. Now, the benefit of doing this is the powers on 25 minus x, well, those cancel, right? This is like saying 3 halves times 2/3. So really, I have isolated this 25 minus x business. And this equals, now I've got 54 times 4 to the power of 2/3. I could rewrite that as what? Well, because I'm doing 2 things here, right? I'm squaring it and I'm cube rooting it. This might be more efficient to go the path of 216. You know what? I'll show you both methods. Why not? I'm feeling happy. Let's say you did calculate that, right? 54 times 4 is 216. Okay? So if you do that, then you would say that this is 216 to the 2/3. Actually, I'll write it right here. 216 to the 2/3. Which means I can rewrite this as cube root of 216 squared. And why am I allowed to do that? Well, I'm allowed to do that because the nth root, or sorry, so a to the m over n equals the nth root of a to the m. If you know your perfect cubes, you should recognize that 216 is a perfect cube, and it's the cube root of 216 is 6. So this gets me 25 minus x equals cube root of 216, which is 6 squared, which is, of course, 36. So then I will add x to the other side and subtract 36. So I'll do minus 36 from both sides, and I'll add x to both sides. That way I get 25 minus 36. I believe that's negative 11 equals x. And I will box that. Okay? And that should be my answer. Okay. I'll show you another way. Let me maybe perhaps in blue from here. I'll say a different approach, because I value different approaches. So I've got 25 minus x equals 54 times 4 to the power of 2/3. Now, within 54, you see 54, you might recognize that that's divisible by 4. Let me backtrack. It's not divisible by 4. If you're looking at 4 to the 2/3, that's kind of thinking like cube root of 4 squared, right? And the thing is, if I took, or I could think of that as cube root of 4 squared, right? If I had a 2 here and I did 2 times 4, that would make cube root of 8. And the thing about 54 is that it's divisible by 2, because it means it's an even number. So I could write this as, well, 54 divided by 2, you figure out what that is. You'll find that it is 27 times 2 times 4 to the power of 2/3. But then, of course, 2 times 4 is 8. So say this is 27 times 8 to the 2/3. Now, you could actually split these up. You could say that this is 27 to the 2/3 times 8 to the 2/3. And the reason I'm splitting it up this way is because these are very simple cube roots to know, right? The value in this approach is, well, maybe I didn't know that 216 was a perfect cube, right? If you didn't know that and you didn't have a calculator, how could you go about doing it, right? And you might say, well, 216, 6 cubed. Come on, Mr. Spake. I could figure that out. But what if it was like 17 cubed? Would you recognize that? Maybe, maybe not. What's nice about this approach is you're really breaking it down. It is more work, but you're breaking it down so it's smaller pieces, which means it's a lot easier to figure out without a calculator. I'll now write these as cube root of 27, quantity squared, times cube root of 8, quantity squared. And that, of course, is still using that gold rule I listed here. It's for here, and it's between these two steps right here. That's what I'm using. Now, we know those cube roots, right? The cube root of 27 is 3, and that's getting squared, times the cube root of 8 is 2, and that's getting squared. So that's equal to 9 times 4, which is 36. From here, you could take this 36 and continue this process. Continue. Sorry, that is the worst continue I've ever written in my life. I'm going to write that again. Continue from here. Okay? Okay, there we go. Now, I am so satisfied. That was so much fun. That was such a good problem. So, yes, the red approach, what's all in red, that is quicker, that's faster, and easier, really. But I like to show you the blue approach on the right because, yes, it is a lot of manipulation, but sometimes this kind of manipulation can take a very, very difficult problem, break it into smaller pieces, and make it easier to solve. All right? But, of course, if you knew your perfect cubes or if you had a calculator, the red is probably the better approach. Okay? But we value all the different types of ways we can do this. Okay, let's now look at example 4. Using a square root in disguise. What does that mean? What? Okay, well, notice I've got my radical here. It's already isolated. It's raised to the power of 2/3. So to do this, to get rid of that exponent, I need to raise both sides to the reciprocal power, right? The reciprocal of 2/3 is 3/2. So I'm going to raise both sides to 3/2. Now when I do this, this will sort of undo the exponent. I'll get 4x plus 1 equals, and ta-da, okay, 8 to the power of 3/2. Well, I could think of that... How would you like to write that? Do you want to do that square root of 8 cubed? That might be a better option than cubing 8. I don't actually know what 8 cubed is. So let's do that. Let's do square root of 8 cubed. Okay? Now, I know I can take out a bunch of 4s here, right? This is equivalent to 8 times 8 times 8. Which you can pull out a bunch of 4s here, right? 4 times 2 times... Well, it's 3 4s and 3 2s, right? In fact... Oh, man, there's so many ways I could write this. I'm just like... My brain is just like, oh, there's so many ways I could just... Oh, it's just perfect. It's just so wonderful. How many different approaches you could do this. And I can't decide... Well, I'll just do this. 3 4s and 2 2s. I'm sorry, I'm just having so much fun with this problem. Do you see that, right? I've split up each 8, but I've kind of like reorganized it so all the 4s are together. But notice that 2 times 2, that's another 4. So that's 4 times 4 times 4 times 4 times 2, right? And... if you think about this, right, this 16 times 16, right, you can think of this as 16 squared times 2, which means you can pull that out and say that that is 16 root 2. Right, because you're taking the square root of 16 squared, so it splits off like that. And so we'll drag down that 4x plus 1, and we shall solve. So to solve, I need to do -1 from both sides. Let's get some more space here. Let's go up here. Okay. I'm subtracting 1 from both sides. That way I get 4x equals 16 root 2 minus 1. And I will divide by 4. And so if I simplify that, I get x equals 16 over 4 is 4. So this is 4 root 2 minus 1/4. And that is my answer. And I will box that. And you say, hooray! That's really no different from what we were doing in the previous example, though. So why did you bother doing this little exercise? I say, hold on. We did something. We did something wrong. We did something wrong. Can you find it? Do you know what it is? Maybe pause the video, give it a wonder about it. Okay, I'm going to spoil it. I'm going to type this in, actually. 4x plus 1 to the 2/3 equals 8. I'll say 4x plus 1 to the power of 2/3 equals 8. Whoa! Hold up. Desmos gives me 2 answers. And if you don't understand those vertical lines, you could think of this as like plotting another line, y equals 8. Notice, there are 2 points of intersection here, not 1. That means there's 2 solutions to this equation, not 1. So what happened? What happened? What did we do wrong? Can you guess? It all happened at this step right here. When I raise this power to the 3/2, what are you doing? Think about what you're doing. I say, what am I doing? Well, the numerator, I'll say the numerator is cubing. What's the denominator doing? The denominator is square rooting. You say, why does he say that so sinisterly? I say, because if I have x squared equals 25, and I take the square root of both sides, what do you have to remember? What must you remember? Plus or minus. You have got to have that there. And that's what we forgot. You see, I call this a square root in disguise because you're saying, oh, hooray, I've raised x to the 2/3 to the 3/2, and the exponent is gone. Hooray. But the thing is, raising something to the power of 3/2, well, the 3 is cubing it, but the 2 is square rooting it. And because you're taking a square root as an operation, you got to have plus or minus. And that means all of these answers, every single one of these radicals needs a little plus or minus in front of it. You have to have that plus or minus. And now we have the right answer. Okay? Now you have the right answer. Okay. By the way, I have not done this in example 3 or example 4, but do you recall all this year we have been checking for extraneous? Well, you kind of want to start doing that again. Because when you work with these square root functions, you can't take the square root of a negative. Particularly if you have an even index function, you definitely should check for extraneous solutions. Now, cube root, you might be able to get away with it because we can take the cube roots of negative numbers, but you got to be careful with square root, and I would just check with extraneous every single time. Now, I'm not going to do that here, per se. One, that would just be a little bit waste of this video time, but 2, this is where I'm going to let you use the calculator, okay? Because I don't want you plugging in 4 root 2 minus 4 by hand and checking that. A quick calculator check will verify that that is true, okay? True. All right, let's move on. Okay, here we go. Example 5 and example 6. Is it going to get a little bit harder? Although that one might be tricky, I don't know. Maybe that last one was the hardest, I don't know. Okay, example 5. What do I do if I have a variable inside the radical and the same type of variable outside? Oh no, oh no. What do I do? Well, don't combine it, that's for sure. You certainly can't shove this guy in here. That is a big no-no. So don't be doing that. Well, let's think for a minute, right? I've got x on the outside. I can't really figure out what x is if it's underneath this square root, right? I got to get it out of that radical. Meaning, since x is in the radical, we need to use exponents, right, reciprocal powers, to undo this radical. We need to square it somehow. But I'll tell you, if you square both sides as they are right now, you're going to make this ugly, really ugly. Imagine taking x minus root x plus 15 and squaring that nonsense. Hideous, atrocious. Do not do this. Rather, if I were to have the square root alone, and then I were to square it, well, then it'd be a nice pretty number, right? That would take away the root easy. So what I'm going to do is isolate the radical. Isolate the radical. I'll do this by adding the square root to the other side and subtracting 5. So you see if I do x minus 5 equals square root x plus 15. And that was just moving stuff over to the other side, right? Now that you've done this, you can square both sides, okay? So now I'll do x minus 5 squared equals, I don't like that equals, equals square root x plus 15 quantity squared. Now, before I continue, I want to take a quick note. I might say note. Not if I square both sides, right? It is not x squared minus 5 squared. It is x minus 5 squared. When you raise this to the power of 2, you have to raise the entire side of the equation because you are essentially multiplying this equation by itself. You can't just distribute a 2 here and here and say, oh, I'm squaring. No. That's not how squaring works, okay? So just be careful with that. All right. Now, once I square this, I've got x minus 5 squared equals x plus 15. And guess what? That's a quadratic. Yes, we've ventured back into the realm of solving quadratic equations, which means you should be able to take it here from here without my help, right? You should be able to say, oh, well, x minus 5 squared, I could expand that. So that's x squared minus 10x plus 25 equals x plus 15. And then to solve a quadratic, I simply just move it to the other side, right? Minus x minus 15. Minus x minus 15. Yielding x squared minus 11x plus 10 equals 0. And is that factorable? Is it? I don't know. Can you factor that? 5 and 2? 10 and 1. Hey, buddy. Look at that. 10 and 1. This is factorable. X minus 10, x minus 1 equals 0. Therefore, right, so x equals 10 and x equals 1. Done. Except not done, actually, because what did I say? Check for extraneous. And you have not done that yet, have you? You say, no, Mr. Spick, I haven't, because you're the one doing the problem. I say, yes, true. So we're going to take it and say, all right, star, check for extraneous. You want to do this, and here's why. Let's actually go do that. So I'll draw a little arrow like this, maybe. Okay. So I've got x minus root x plus 15. I don't like how I'm writing that. It's ugly. Root x plus 15 equals 5. So, plug in x equals 10. Then 10 minus root 10 plus 15, does that equal 5? Question mark. Well, that's 10 minus square root 25. And 10 minus root 25, well, that's 5. And so 10 minus 5 equals 5? Yes. True. True. I might even say that. True. So I've tested x equals 10. Yes. But now let's test plug in x equals 1. So now if I'm using that same equation, 1 minus square root 1 plus 15 equals 5, question mark. Well, that's 1 minus square root 16. And that's 1 minus 4. Is that true? Does 1 minus 4 equal 5? No. That's false. So, I'll end it all off with, therefore, x equals, and I'll put a little solution set like this, 10. That's my only answer. You see, 1 is an extraneous solution. It's an extra answer, but it doesn't actually work. Once you plug it back into the original, it fails. So that check for extraneous comes back in this unit. I believe it comes back in a lot of other units too. So you got to remember to do that, okay? Yeah, I'm sorry. I know it's not very fun to check for extraneous. Again, like in the past, you guys can do this on the calculator because I'll be giving you the calculator for you to be able to check for extraneous, okay? That's why that'll be there. Okay. And now example 6. I call it your worst nightmare. It's not really the worst. It's actually fine. But I thought that was funny. Not one radical, but 2 radicals. Eek, right? So, how do we deal with 2 radicals? Yeah. Well, you can kind of take multiple approaches. You kind of had to just get creative here. But I'll tell you this. You want to isolate the most complicated radical. So I might say that. I know that sounds kind of funny. Not notice. Isolate the most complicated radical. Why do this? Well, let me show you. If you look at these, right? What is worse? Taking square root of 3 minus x plus 1 and squaring that? Or looking at square root 2x minus 1 and squaring that? This is the easier option. Easier option. And that's because the radical isn't as complicated as the other one. So let's isolate the more complicated radical. And when I say complicated, I just mean it has a bunch of terms in it. Who's to say that 3 minus x is more complicated than 2x, right? I think it's more complicated because when you start adding and subtracting inside radicals and you have a bunch of terms under a root, that's just ugly and it's going to be hard to deal with. Versus if it's just 2x, well, we can work with that without too much headache. So here's what we're going to do. We say root 3 minus x equals root 2x minus 1. Now, let's get rid of one of these. It's not guaranteed that we're going to get rid of both radicals. So I'm sorry, but you'll just have to bear through that. So let's take this guy And now we'll square both sides. I'll square this guy, and I'll square this fella, like so. Now I square the left side. It's now 3 minus x equals, well, you might want to distribute this. I might write this out by hand, unless you've got really strong mental math skills. Let's distribute this ugly mess, yeah? Let's do gold. Root 2x times root 2x. Well, that's kind of like saying root 2x squared, isn't it? So that's just 2x, right? You're multiplying two roots, so that's equal to 2x. Then 2x times negative 1, that's minus root 2x. And then another one, right? Minus, again, minus root 2x another time. And then finally, negative 1 times negative 1, which is positive 1. Okay. Let's combine like terms and see if we can't, make something of this. I'll put a little star. Combine like terms. This is just to simplify the problem and see if we find anything useful. So I'll add x to the other side. So this side's going to become 0, the left side. Add x to the other side becomes 3x. Minus, I've got 2 root 2x's. So I'm going to say minus 2 root 2x. And then if I subtract 3 from 1, that's minus 2. Okay. Now what? What do you think, right? How do you want to go about doing this? Is there a quadratic pattern here? Let's not do that. I don't want to overcomplicate this. So I still have a radical, which means isolate the radical again, right? Essentially what we've done is we've reduced the difficulty of this example back to example 5, right? Because now I have one variable and one variable inside the radical, just like a variable inside the radical and one on the outside. So I'm kind of going to use the same exact approach. So I will isolate radical again. And so if I do that, that's really just effectively adding 2 root 2x equals 3x minus 2. Okay? Okay. Draw a nice arrow here, like so, and we'll continue. And I'm just going to rewrite it again. 2 root 2x equals 3x minus 2. Now, how do we get rid of that square root? Okay, look. This is where I don't want to go back on my word. You see, I didn't actually fully isolate the radical. To truly isolate it, I would need to divide by 2. But I'm actually going to recommend that you don't do that. And here is why. Squaring that is just no. No, thank you. I reject that. Thank you. I would rather we just square both sides from here. And when we square both sides, we'll just be really careful. Yeah? This is 2 times 2x, root 2x, times 2 root 2x. And then this over here is 3x minus 2 times 3x minus 2. So 2 times 2, that's 4 times root 2x times root 2x is, again, 2x. So that equals, let's distribute this nonsense. Hooray. 3x times 3x is 9x squared. And then minus 6x. Uh-oh. Jocelyn, don't talk right now. Stop. Do not disturb. I can't have her messaging me right now. Minus 6x. and then plus 4. Not that I don't love her. I want to talk to her desperately. I really do. I love her. But I'm filming a video right now. We can't have her messages. 4x times 2x is 8x equals, then this is 9x squared minus 12x plus 4. So let's subtract 8x. Yeah. We'll isolate this quadratic. Minus 8x from both sides. Getting me 0 equals 9x squared minus 20x plus 4. And this is my quadratic to solve. And now I'm thinking, is this factorable? It should be. I think it's factorable. Let's try it, okay? Remember, because we're back in the realm of quadratics now, right? You and me, we're on the same page. I mean, the lesson's pretty much over. From here, you should be able to take it. This would have been on a Unit 5 test, right? I'm going to see if this is factorable. I'm going to try factor by grouping. I actually don't know because I haven't worked this problem ahead of time. 9 times 4 is 36, and down here's negative 20. Do two things, add to get positive 36 and negative 20. Well, there's 9 and 4. 6 and 6. Okay. 6 times 6. 9 times 4. Oh, 18 and 2, huh? Look at that. 18 and 2, where both are negative. Oof. There we go. Yeah. So this will factor, right? Okay, yeah, I'll just keep 0 equals. This factors, okay, so 2 factor by grouping. 9x squared minus 18x minus 2x plus 4. This is 0 equal to, factor out the GCF, that'll be 9x, and this is x minus 2. Now factor out a negative 2 here, so that it's x minus 2, meaning this factors as 9x minus 2 times x minus 2, which tells me, so x equals 2/9 and positive 2. And I get that from setting the factors equal to 0, right? And so now, you have to check for extraneous. Okay? Yep. Check for extraneous. So do I even have space to do this? Okay. I'm going to try. What's my function? Oh boy, I'm just having fun. Root 3 minus x. You say, Mr. Spake, will we be tested on this? And I grip my teeth and I say, yes. Yeah, you will. Yeah, you will. Okay. So let's check this. Let's put in 2/9. Does square root of 3 minus 2/9 equal square root of 2 times 2/9 minus 1? Question mark. No, I don't think so. And you say, how do you know that? And I say, numerical intuition. That's how I know. I just know that it's not true. You can use a calculator, all right? Plug in the left side, plug in the right side. They're not equal, okay? No. Oh, let's write a better no. No. So 2/9 does not work. Let's plug in 2, though. Square root 3 minus 2 equals square root 2 times 2 minus 1, question mark. Look at that. Square root of 3 minus 2, that's square root of 1. And then that's root 4 minus 1, which means 1 equals 2 minus 1. Question mark? Yes. Okay. So, therefore, I'll just put this here. Therefore, x equals, not 1, sorry, 2. And that is my solution. Ooh, that's hideous. You know I like those nice rectangles. Let's try that one last time. Okay. Wow. That was fun. That was just a grand old time, wasn't it? That was fantastic. Okay. Anyway, so that's it for this video. I know it's probably kind of long. Example, you're feeling good about example 3 and 4 now, aren't you? You're saying, oh, you know what? I think I was judging example 3 and 4 a little too harshly, because after example 6, I just don't know if I want to continue. And you say, you keep going, don't give up. You'll be good. All right. So hopefully you made it to the end of this video. Thanks for being here. And we will talk about this more in class and get some more practice, all right? Don't be too scared. You know this stuff, right? Notice most of that was really just working with quadratics. It wasn't even really dealing with radicals. So it's really just using prerequisite knowledge into this new context. So, all right, I'll see you around, and have a good day.